Hi everybody, it's Paul again. So the next bit we'll be looking at is the idea of linear discriminants. So we want to talk about this before we get on to the perceptrons and the multi-layer perceptrons, because this is the simplest case. So what we're trying to do is just really define a linear discriminant function as just a straight line that separates two classes of data. And we're defining it as y, which is where we are, equals the set of weights multiplied by the x values plus w0 a bias. And the idea is if the value of this function is greater than 0, then it's in class 1. If it's less than 0, then it's in class 2. And of course, there's always the issue about if it is equal to 0, which class do we use? So defining this, we're essentially defining a hyperplane that separates the data. So in 2 dimensions, this will be a line. In 3 dimensions, a plane, but regardless, it's just straight. So the W vector is giving the orientation of the hyperplane, and W0 gives the location of the hyperplane. And we can look at the distance from the 0 point, the origin, in that way. So it looks like this. You remember these slides a little bit from the support vector machine. And the support vector machine lecture, the support vector machine solves this in one problem. The linear discriminant function solves it in a slightly different one. So we've got the green line is our hyperplane. So we've got our red points on one side and the blue points on the other. And this one's x is 2-dimensional. So for when the value is greater than 0, we're in the blue region. If it's less than 0, we're in the red region. W gives us the direction, where the hyperplane sits, and W0 is where it's placed. So this approach to classifying is really, really straightforward and really simple, and it scales up to the multi-category case fairly easily. So the trick though is we need to work out what values of the weights and what the bias, the W0, should be. So we looked at different ways of doing that before, and I think we talked about using sum of squared errors before. So that W0 is a bit of a pain because it makes the maths a bit yucky. So we can clean it up. So the idea is we just make we have an x tilde, which is the old x vector, but we have a new initial value, which is always set to 1. So it's 1 and then the x. So it's 1-dimensional more than the x values were. We have a w tilde that just puts that W0, the bias, as the first value. So, and then when we want to work out the Y value, all we need to do is multiply the W and the X vectors, the W tilde and the X tilde vectors together, and it makes things simpler. So we don't have that horrible plus W0 anymore, because we do have it as W0 times 1, which of course is W0. So this is just a simple way to clean the maths up. So there's the idea of linear separability, which we talked about when we looked at the support vector machines as well. So the idea is if the data from the two classes can be separated with a hyperplane, then it's said to be linearly separable. And if that's not the case, then the linear discriminant function can't classify the data without making some errors. And linear separability will be important when we look at the perceptrons a little bit later. So we can think about the weight vector W as specifying some point in a weight space. And there's the idea that the data points in our X constrain where that weight vector can lie. So there can be lots of places, lots of ways to specify W, the weight space. There can be lots of potential hyperplanes, so we need to choose one of them. And one approach to doing it is to choose the one that has the widest margin, the widest gap between the two classes. And that's the approach that you'll remember that we looked at with the support vector machines. What we're going to use instead is the method of least squares. Here we're trying to maximize the minimum distance between the samples and the line, the hyperplane. So least squares looks like this. We want to have an error measure for a particular weight vector, because remember the x's are essentially constants for the whole thing. So we have an error based on the weight the weight vector, which is the thing that can change. So we've got the squared error. So that yn function x blah 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 w is just the prediction that is the prediction that the linear discriminant would make. We subtract the target, so it's either +1 or -1, and then square that. That will give us the error for that one xn pattern. We sum that up for all of the patterns. That gives us and then divide by 2. That gives us essentially the squared error for all the patterns for that set of weight vectors. And then we need to find some way to minimize that error term. So one way of doing it is to use, so one way to minimize the sum of squared errors is to use gradient descent. We've seen this before as well. So the idea is to change the individual values of w just a little bit in the direction that minimizes the error. So we want to move towards a way that minimizes the error. So there's a really straightforward kind of algorithm to do that. So we start with the initial value of w that's random, and then we're going to loop until we're done. And what we're going to do in each loop, we're going to assign the value, the new weight, to be the old weight minus a little bit of going in the direction that minimizes the error. So the partial derivative of the error with respect to w tilde evaluated at w tilde is going to give us the direction that that increases the error. We want to use minus that, which will be the direction that goes towards less error, but we don't want to go totally in that direction all in one go. So we have eta as a learning rate, which is just a small value, maybe 0.1, that just goes a little bit in the direction that goes towards minimizing the error. The reason we need to do that is because that partial derivative can be a really curvy kind of thing, and if we go too much in one direction, we might we might go too far in the wrong direction. So we keep on doing this. We start with the initial random weights, we update the weights just a little bit to go in the direction that minimizes the error, and we just do that many, many times until the amount that we've updated has gone less than a particular threshold, which means that we've essentially hit the minima. Could be a local minima, and that's one of the problems of gradient descent, but there's ways around that as well. So that's all we're going to talk about in this section. We'll have another section in a second.